Hello everyone, this is group number 30, Computer Science and Engineering batch presenting on the topic A Simplified IoT Architecture. I am Ananya Kashyap. The other group members are Aravind Unnikrishnan, Nagasai Kiran Karra and Saloni Choure. So here I proceed. What is IoT? The Internet of Things is a system of interrelated computing devices, mechanical and digital machines provided with unique identifiers and the ability to transfer data over a network. In a simple way to put it, you have things that sense and collect data and send it to the Internet. A typical IoT solution is characterized by many devices that may use some form of gateway to communicate through a network to an enterprise backend server, which is running an IoT platform. IoT architectures may differ depending on the industry use cases or the technology deployed. In common, all the frameworks recognize the interconnection of the IoT endpoint devices to a network that transports the data where it is ultimately stored, used by the applications, whether at the data center, in the cloud, etc. A typical IoT architecture can be viewed containing a number of layers, consisting the entire model. Each of the layers can be constructed independently of one another. The commonality between the various IoT frameworks is that they all recognize the interconnection of the IoT endpoint devices and the data center. The framework is presented as two stacks parallel to each other. They are the core IoT functional stack and the IoT data management and compute stack. This is a typical simplified IoT architecture. The core IoT functional stack consists of layer structures. These are applications, communications network, things, sensors and actuators. IoT data management and compute stack consists of layers, cloud, fog, and edge.
The framework presented here separates the core IoT and data management into parallel and aligned stacks to give an understanding of both the network and the applications at each stage of a complex IoT system. The core IoT functional stack has three layers: things layer with sensors and actuators, communication network layer, and an application layer. The core IoT data management and compute stack also has three layers: edge layer, fog layer, and cloud layer. And security is central to the entire architecture. It is provided throughout the stacks for all the layers. The core IoT functional stack can be expanded into sublayers containing greater details. For example, the communication network layer can be broken down to four sublayers, namely the IoT network management layer, network transport layer, gateways and backhaul network layer, and access network layer. The access network layer has its own protocols: FAN, LORA, and PLC. Similarly, the IoT network management layer will have COAP and MQTT. The application layer of an IoT network is different from the application layer of a typical enterprise network. IoT often involves strong big data analytics components. Hence, the analytics sublayer in the application layer, along with vertical specific application sublayer, has been included. As discussed before, the IoT core functional stack has three main layers. The things layer is the physical layer which has sensors for sensing and gathering information about the environment. At this layer, the physical devices need to fit the constraints of the environment in which they are deployed while still being able to provide the information needed. The second one is communications network layer, which is responsible for connecting to other smart things, network devices, and servers. Its features are also used for transmitting and processing sensor data. The last one is application and analytics layer. The application layer is responsible for delivering application-specific services to the user. At the upper layer, an application needs to process the collected data to make intelligent decisions based on the info collected and in turn instruct the things or the other systems to adapt to the analyzed conditions and change their behaviors or parameters accordingly. In data management and compute stack, edge layer is aligned to do data management with the sensors themselves. Fog layer is aligned to do data management in the gateway and transit network. Cloud layer will perform data management in the cloud or central data center.
Problems with the traditional IT cloud computing model in the IoT. The first problem is that latency will be greater because the collected data needs to be sent to the data center through the backhaul network, which might consist of thousands of nodes. In some cases, milliseconds matter for many types of industrial systems, such as when you're trying to prevent manufacturing line shutdowns or restore electrical service. Second problem: higher network bandwidth. It is not practical to transport vast amounts of data from thousands of edge devices to the cloud, nor it is necessary because many critical analyses do not require cloud scale processing and storage. For example, offshore oil rigs generate 500 GB of data weekly. Commercial jets generate 10 TB for every 30 minutes of flight. Real-time processing. IoT data is increasingly used for decisions affecting citizen safety and critical infrastructure. So analyzing data close to the device is important. One solution is that we can introduce fog nodes. Any device with computing storage and network connectivity can be a fog node. The fog node sits as close to the IoT endpoint as possible to deliver distributed computing. From the perspective of fog nodes receives feeds from IoT devices using any protocol in real time, and we can run IoT enabled applications for real time control and analytics with millisecond response time. It provides transient storage, often 1 to 2 hours, and sends periodic data summaries to the cloud. And from the perspective of cloud, it receives and aggregates data summaries from many fog nodes, and it performs analysis on the IoT data and data from other sources to gain business insights. Applications of fog computing. It provides support for mobility. For example, air pressure tracking on a truck and this fog node installed on the same truck itself, thereby sending only the relevant information to the cloud. Fog computing in smart cities. Large cities face a number of challenges, including public safety, sanitation, traffic congestion, high energy utilization, and municipal services. The solution to these challenges lies in a single IoT network by installing a network of fog nodes. And data from these sensors must be watched to find what actions are required. For suppose, triggering a fire alarm if smoke is sensed. In case of video cameras in public places, the bandwidth of visual data collected over a large scale network makes it impossible to carry the data to the cloud and collect real time insights. Characteristics of fog computing: real time interactions and low latency, deployment near IoT endpoint. Fog nodes are typically deployed in the presence of a large number of IoT endpoints. Geographic distribution. Fog network distributes geographically its nodes and sensors in the scenario of different phase environment. For example, temperature monitoring at the chemical lab. Wireless communication between the fog and the IoT endpoints. Although it's possible to connect wired nodes, the advantages of fog are the greatest when dealing with large number of endpoints, and wireless access is the easiest way to achieve such scale. Interoperable. Fog components must be able to work in interoperating environment to guarantee support for wide range of services like data streaming and real-time processing. Heterogeneity. Fog nodes can be deployed in a wide variety of environments.
Edge computing. Edge computing is a part of a distributed computing topology in which information processing is close to the edge, where these things and people produce or consume that information. At a basic level, it brings computation and data closer to devices where it's being gathered rather than relying on a central location. Edge computing was developed due to an exponential growth of IoT devices, and these devices generated enormous amounts of data during the course of their operations, which is why not only the quality suffered due to latency, but also the costs in bandwidth were tremendous. Edge computing devices help solve this problem by being a local source of processing and storage. Devices include an IoT sensor, a computer, smartphones, etc. Benefits of edge computing. The biggest benefit of edge computing is the ability to process and store data faster, enabling more efficiency. The other benefits include cost savings, interoperability, reliability, and security and compliance. The hierarchy of edge, fog, and cloud computing. This model suggests a hierarchical organization of network, compute, and data storage resources. At each stage, data is collected and analyzed according to the capabilities of the resources at each level or layer. The advantage of this is that a response from resources close to the end device is fast and can result in immediate benefits while still having deeper compute resources available in the cloud. When architecting an IoT network, we should consider the amount of data to be analyzed and its time sensitivity. Understanding this, we can decide whether cloud computing is enough or edge or fog computing would improve efficiency. It not only avoids the need for costly bandwidth additions but also protects sensitive IoT data by analyzing it inside the walls itself. Thank you.